We continue with our discussion on information theoretic lower bounds in Unit 8, and till now what we have seen is two information theoretic lower bounds. One for the randomness for the source coding problem, and second for the Stein's lemma. In proving a lower bound for the source coding problem, we used Fano's inequality. And in proving the lower bound for Stein's lemma, we use a data processing inequality. In fact, Fano's inequality itself is derived using a data processing inequality, but the one we used in Stein's lemma is a slightly different data processing inequality. In this third lecture on this topic, in this unit 8, I will now look at lower bound for randomness generation. So, unlike our previous two lower bounds, this lower bound will essentially rely on the continuity of entropy function, the continuity of entropy. Okay. So what is the randomness generation problem? The goal, so we are given a random variable x, and the goal is to generate uniform randomness from x. Okay, so more formally, we seek a mapping f from x to 0, 1, L, so it's L bit output. And what we want is that the total variation distance between the output of this mapping, f of x, when applied to the random variable x, and a uniform distribution. So this guy is uniform on 0, 1, L. This total variation distance, we want it to be less than equal to epsilon. That's the goal. Question is, what's the largest such L that we can get? That is the question. The largest L that we can get, such that the probability distribution of fx is as close to uniform on L bits as possible. Is within a distance epsilon from uniform on L bits. So we have already seen a scheme for this case. What we have seen is the following. What we have seen is that, let me first denote this largest L by something. Let L star epsilon, maybe I should just use L star epsilon p. This is something I'm defining right here. Is the largest L, max over L, such that you can find a mapping f as above. So there exists f from x to 0, 1, L such that d of p of x and a uniform distribution is less than equal to epsilon. The largest such L is what we are calling L star epsilon x. What is the largest number of bits that you can extract? That's something we would like to understand. Now, what we have seen earlier is a scheme. So we saw a scheme which gave us that L star epsilon p exceeds something. So what was the lower bound that we gave? It is the maximum. It's the maximum over of maximum of. That theorem was a little bit technical. What we saw was that it's the maximum. We end up getting 7 by 2 epsilon. Okay, so I'll just put 7 by 2 epsilon so that you can go back and compare. But it doesn't matter, the 7 by 2 is not important. You can absorb it here also. Is greater than maximum over lambda such that the probability that x minus log px is greater than lambda, this probability exceeds 1 minus epsilon. Okay, so if you have a large probability, lower bound on minus log px is the lower bound is under p, the distribution p. This maximum over lambda is an achievable lower bound. Is greater than 1 minus epsilon. So there is some small loss. So this epsilon here boils down to uh, 7 epsilon here, and in fact the length that you attain is not exactly lambda. It's also a small back off from lambda. I think it was the final length. Just 1 second, I'll think about it. So the final length was correct. It was, so this was lambda um, minus log 1 by epsilon. Okay, that's the length, right? So if you have this, then you get this. Okay. So this is roughly by again by Chebyshev's inequality. Sorry about this. Let me make some more space. Somehow this pen loses its calibration quite rapidly. By Chebyshev's inequality, one estimate for this lambda, the lambda which satisfies this, is h of x. So we want this to exceed lambda with large probability. X here is p. H of p minus square root variance of minus log px divided by epsilon. Okay, so this is the estimate minus log 1 by epsilon. So this L star of 7 by 2 epsilon p is this much. Okay, so we get, this is the bound which we saw earlier, and so this brought out the role of entropy in randomness generation. It says that roughly you can generate as many bits of randomness as the entropy minus some correction term which depend on epsilon. This epsilon, the gap that you are allowing. In fact, this dependence on epsilon can also be improved, as I have been saying again and again. We use Chebyshev inequality, but if you use Chernoff bound, this dependence can be improved. And also for i.i.d case, this thing is additive, and we get more refined estimates. Okay, maybe I'll just note down what happens for i.i.d distribution. Okay. For i.i.d distribution, so you don't have one sample from X, but i.i.d's n i.i.d samples from P, i.i.d samples of X, i.i.d copies of X. Okay, so this guy now, same bound I'll apply, NHP. Once again, variance is additive because this is sum of independent random variables, so it's just n times variance of minus log px1, say, by epsilon, and minus log 1 by epsilon. So the leading asymptotic term is this guy here. Okay, so leading asymptotic term is this guy here. Okay, so the leading asymptotic term is NHP. Okay, for i.i.d recording, for i.i.d observations. So is this NHP any tight? That's what you want to understand. Is this so? By the way, this asymptotically, if you divide this by n, I mean we can ask again this question, asymptotic question, in the spirit of what Shannon studied. So we can start with this 1 by n, the maximum number of bits that you can extract for any epsilon. By the way, I can now just put it as epsilon here because the 7 by 2 or whatever it is can be assumed, can be subsumed here by replacing it with 2 by 7 epsilon, and that's just some small factors here. Okay, so this guy here is greater than equal to HP, and this holds for every epsilon. Okay, so every epsilon between 0 and 1, this is true. So how do we show that this is tight? And that's the goal now for us. We want to derive a lower bound to show that this particular bound is tight. So how do we show this? So here is we once again will derive a single shot lower bound. Okay. So we know that L is equal to entropy of a uniform distribution. Okay. On, so this guy is uniform on 0 1 L, and this distribution P f of x is close to this uniform distribution. Therefore, by continuity of entropy, the bound that we derive, this HP uniform minus H fx okay, is less than equal to mod of this is less than equal to what was the bound we had? We had total variation distance between P fx P uniform log cardinality of the output, which in this case is cardinality of this support, which in this case is just L, minus the binary entropy of d fx uniform. Note that this is less than epsilon, and epsilon, let's say, is less than half. Assume that. Therefore, this binary entropy function, which looks like this is increasing. So this guy, if I replace it with epsilon, this will only increase. Making a mistake here, just 1 second. Oh, sorry, this is plus. And this guy is H epsilon. Okay, this is just the continuity of entropy bound. Okay, so so that's great. So this we have that H of P uniform must be less than H of fx plus epsilon L plus binary entropy of epsilon. But since this is something that we have been using again and again, this is something you should show. I'll give a homework assignment for this. The entropy of f of x is less than equal to entropy of x, the random variable x. So by combining these observations, what have we shown? We have shown L is less than equal to entropy of P plus epsilon L plus H epsilon. That is L, I'll take this 1 minus epsilon here, is less than HP by 1 minus epsilon plus H of epsilon by 1 minus epsilon. Okay, that's the bound that we have. Of course, if you have again i.i.d. observations, so by the way, so this is true for every L, so this is also true for L star epsilon P must be less than HP by 1 minus epsilon plus H of epsilon by 1 minus epsilon. Okay, that's the bound. We can compare it with the lower bound, which is this one here, H of P minus some variance thing, minus log epsilon, and this one is a multiplicative change by epsilon. So for i.i.d. case, let's just look at that case. So firstly, this is great. Entropy shows up here also, but there is this 1 minus epsilon. This is happening in many of our bounds. In fact, it's very interesting to get rid of this 1 minus epsilon, the multiplicative loss of 1 minus 1 by epsilon. And typically you can, in this case specifically for sure, but in general, you can replace this multiplicative loss with an additive loss of log 1 by 1 minus epsilon in many applications. So what happens for the i.i.d. case? So this Pn, suppose we are interested in this guy, and we are interested in the asymptotic quantity here, and let's say we also allow vanishing accuracy. Then first this guy is bounded by n times hp, which will be divided by n. So you only get n times hp by 1 minus epsilon plus h epsilon by 1 minus epsilon n. So in the limit as n goes to infinity, this term goes to 0. So this is what you have. And then you can take limit epsilon going to 0. So this is equal to hp. So this is less than equal to hp. And we already saw that this is greater than hp. So this must be equal to hp. So we have shown a matching tight, asymptotically tight lower bound. So that's one result. Limit n going to infinity 1 by n L star epsilon Pn, limit epsilon going to 0 is exactly equal to hp. Asymptotically, you can extract as many random bits from an i.i.d. sequence with common distribution p per observation as the entropy of p. This is per observation. Okay, that's the result. So once again, using information theoretic methods, we can not only come up with a scheme, but we can also show its optimality. It's a sort of precise performance optimality. Okay, so this is all I want to say in this lecture, and I'll see you in the next lecture.